Arrangement of clubs and diamonds. So this is another one of those problems where we ask you a question, we give you a proposed solution, and then you have to try and figure out if there's anything wrong with that proof. So in other words, it's one of those, is this proof legit type of questions. So the question we're giving you is, how many ways are there to arrange C clubs and D diamonds, where C and D are natural numbers greater than or equal to 0, so that all of the clubs are consecutive? So this would be a good time to pause and try and figure out the problem yourself, which might actually make finding any flaws in the proposed solution easier. Okay, so the proposed solution states that you can have any number between 0 and D diamonds, then a string of clubs, and then the remainder of the diamonds. So there are D plus 1 possibilities because you could have set down between 0 and D diamonds. Another way you could phrase this is using a multi-step process, which you might be more familiar with through concepts or previous classes. So this is when you have a counting problem, you create a list of steps to create the arrangement you want, and then for each step, you note the number of ways that step can be done, and then you multiply all the number of ways. So we can also visualize this with a small example. So we can pretend, let's say we have D equals 5 diamonds and C equals 3 clubs, just so we can visualize what's happening in this multi-step process. So step 1 would be to set down all the D diamonds. And there's really only one way you can set them all down. In our little example, we just set down all 5 diamonds. Then the next step would be to pick a spot in between the diamonds to set down all C of the clubs. So in our little example with 5 diamonds, we note that there are 6 different slots where we could insert the C clubs. In other words, there are D plus 1 ways to pick a spot. So let's say we pick this spot right here. So this is where we're going to go ahead and insert all of our clubs to create our arrangement. So there was one way to set down the diamonds, D plus 1 ways to pick where the clubs would go, for a total of D plus 1 ways in total to create an arrangement, which matches with what we said before. So now the question is, with this proposed solution, is this proof legit? Is it correct? It's almost correct. Now would be a good time to pause and try and figure out what it's missing. So there's nothing incorrect written in this proof so far, but it is missing something. So try and see if you can figure out what that is. Okay, the step it's missing is the corner case when C equals 0. So in that corner case, there's actually just one possibility. You would just set down the D diamonds, and then it doesn't matter what you pick because there are no clubs to set down. With this addition of the corner case, then the proof is complete. So you might be thinking this was kind of like a trick question, you feel like it's not really applicable. But the really important takeaway here is to remember the corner cases. In this specific example, if you had forgotten that corner case, you would have still gotten a majority of the points for the initial proof. But actually, in some cases, the meat of the proof and the interesting problem solving can happen in a corner case. So it's important that we develop the skill of recognizing corner cases and figuring out when they happen. One way to do that is to make sure you know what are you assuming. If you're assuming that the variables in your problem are positive, you might be missing some important negative cases. If you're assuming the parity of some variables, whether they're even or odd, you should be checking the other case. Another place where corner cases often come up is quote-unquote like null objects. In other words, for integers and natural numbers, this could be the number 0, which was the case in our proof. We forgot about when there are 0 clubs. But this can also arise in other cases. When you're dealing with sets, make sure you consider the empty set. When you're dealing with graphs, does the empty graph make a difference? Things like that can also be corner cases. And one other suggestion is making sure you consider the interaction between variables or different parts of your proof. Maybe one part or one variable of your proof checks out, whether or not it's even or odd, it makes sense with your proof. And there's another variable that whether or not it's even or odd, it makes sense in your proof. But perhaps when they're both odd at the same time, something weird happens and you really have to check what's going on. So of course this isn't an exhaustive list, and I don't think there is a way to make an exhaustive list of corner cases. So the general skill you should be doing is making sure you're aware of what you're assuming and constantly questioning your assumptions so you can catch those corner cases on your own.